Hello, everyone. My name is Kip Larson. I'm a Principal Product Manager on AWS IoT Analytics and Applications. And we're here to talk today about how Eric Ferguson and his team at iDevices have been able to get value out of their IoT data using AWS IoT Analytics. This is a relatively new service that we launched recently at reInvent last year. It's currently in preview. This service helps customers deal with what happens after the data gets into the cloud in order to get value out of it. And before I hand the microphone over to Eric, I'll walk really briefly through just a couple of the components of AWS IoT Analytics to give you an idea of why we built the service and what it can do. So at its core, IoT Analytics is a service that processes, enriches, stores, analyzes, and visualizes IoT data at any scale. And the reason that we built this service is that we had customers that were struggling with the fact that IoT data is often noisy, it contains gaps and many false readings. A good example of this is if you have an asset that reports GPS data, about every 10,000th reading that you get will be at latitude 0, longitude 0. And unless your device is slightly off the west coast of Africa, it's likely that that's just a bad reading. And before you feed that message into a complex machine learning model or try and surface it on a map diagram as part of a dashboard, you want to clean that message up. You also find that IoT data is very context poor. It often comes from very low-powered devices that don't report who their owners are, where they may be physically located if they're not a GPS device, and often are lacking crucial data that need to be built into the message or into the data prior to it being analyzed, visualized, or machine learning models being built on top of it. After that data has been cleaned up, enriched, it then needs to be stored. One of the things about IoT data is, especially in industrial contexts, it comes in at very high volume. So a rotor on a conveyor belt might report status 100 times a second. But each message is very small. This leads to very tall, very sparse tables that can be challenging to manage. And so customers needed good IoT optimized time series data storage for their process data. And customers also wanted to be able to use powerful querying techniques to get at this data and visualization and data science tools in order to get value out of the connected device data. In response, we built IoT Analytics. And this service contains a number of components that resolve or solve those challenges, and we'll briefly go through them. In a moment, Eric is going to walk through how his team was able to use these components to get to value. But very briefly, they are the channel. The channel is the front door to IoT Analytics. It organizes information coming from devices that are registered to AWS IoT Core, and it can also read messages from S3 or Kinesis. Once the sources of messages have been grouped together in a channel, the data is fed into a pipeline. This is just a set of sequential processing steps that let you convert data from Fahrenheit to Celsius, apply regex calculations, do simple math, if then else conditional filters, and enrich the data by either going to the AWS IoT device registry or Shadow, or invoke a Lambda function that takes your blocks of IoT messages and enriches them with data based on your own code. Once the data is flown through the pipeline, it gets stored in an IoT optimized time series data store. This is an abstraction across a variety of different storage technologies that we continue to innovate on that are designed to give high query performance and low cost for IoT use cases. After the data has been stored, it needs to be extracted using data sets. Data sets are the result of simple SQL that can be run ad hoc or on a schedule. Once the data has been downsampled into a data set, it's easily available for visualization in AWS QuickSight or through a deeper analysis in a Jupyter Notebook through our integration with the machine learning service Amazon SageMaker. Now I'm going to hand things over to Eric from iDevices to talk about how his team was able to apply these components in order to get value out of his IoT data. Take it away, Eric.
All right. Thanks, Skip, and thank you and welcome to everyone watching. My name is Eric Ferguson, Chief Software Architect at iDevices, and I'm here today to talk to you how to stand up 2 common IoT use cases in under 45 minutes with the help of AWS IoT Analytics. I'll start with a brief intro into who we are and what data we have available to us. I'll describe our ingestion pipeline and then quickly walk through creation step by step in the AWS console, and then using the pipeline implement 2 specific use cases. First up, we have anomaly detection, and then we'll build a dashboard for our marketing and sales team. With that said, we've got a lot of ground to cover, so let's get to it. iDevices was founded in 2010 with the introduction of the iGrow Bluetooth cooking thermometer. In early 2014, we were invited by Apple into the Early Access Program for HomeKit as one of the original 12 launch partners, which drove a pivot from cooking and grilling space into home automation. Fast forward a few more years, we now have 8 products in the market, both plug-in and in-wall devices, primarily around power and lighting and thermostat spaces. In 2016, we launched support for Amazon Alexa in all of our devices and Google Assistant in 2017. With the integration of these services, we have a new stream of usage data to help us better understand another dimension of our customer usage patterns. In April 2017, we were acquired by Hubble Incorporated and are now working with corporate and several sister companies to help drive our technology into even more devices in new domains within Hubble and also other strategic partners as well. Needless to say, with all these new opportunities, the data we have available to us will grow quickly, and so will our use cases. Hence the need to optimize our ingestion pipeline and ensure the tools are in place to handle all sources of data seamlessly. So let's take a look at the pipeline specific to Alexa usage. With each Alexa request from our customers, we gather a few pieces of critical information regarding the request, and we want to store this time series data somewhere that can be queried later on. Ultimately, what we really want is SQL access to our real-time Alexa request stream. The first incarnation of this pipeline was built using 4 different services. Our Alexa CloudWatch logs triggered a Lambda, which posted raw data to Kinesis Firehose, which marshaled the data into Redshift after a brief stop in S3. It worked, but it was a lot of overhead to manage when all we really cared about is SQL access in Redshift. Now with IoT Analytics, we replace all these services with a single service. So now let's take a peek inside the IoT Analytics bubble and take a look at the updated pipeline and how we use it to enable our 2 use cases we're talking about today. Starting from the left, we have our Lambda Alexa skill adapter, which feeds JSON payload into a single channel. From there, we bridge this stream into 2 separate and parallel IoT Analytics pipelines. From the anomaly detector, we simply pass the raw data unmodified straight into the data store. However, the raw data format, as we'll see later on, can be transformed into something more useful and digestible by QuickSight with a few modifications. Luckily, the IoT Analytics pipeline allows us to do this modification in real time, such that we're only storing the post-process data in a separate data store to be directly consumed without modification by QuickSight, which is huge for us, as we'll see in a little bit. So now let's switch over to the AWS console and actually create this pipeline in real time. So the first step in creating the pipeline, as you saw in the previous diagram, is to create a channel. So in our particular case, we'll give it a name, and we give it an MQ topic filter. So this is the MQ topic in which messages will come in from our Lambda function and will feed the channel. Okay, now with the channel, we need to bridge this into 2 separate pipelines. So let's create those. We'll give the pipeline a name. We'll select the data source, the channel that we just created. And now we need to tell the pipeline what kind of data to expect. So we'll upload a JSON document, rather than having to enter in all these fields individually. And because this first pipeline is for the anomaly detector the anomaly detector expects the raw data that we're giving it, we don't need to do any modifications. We'll just pass it directly through to the data store. So we'll click Next. We need to select the data store. There are none currently, so we will create one. and now finish the pipeline. So one branch of the pipeline is created fully end-to-end from channel all the way into the data store. So let's create the other pipeline, which will drive the marketing dashboard. And in this particular case, we'll actually need to do a couple of modifications in it. So we'll give this one a name. Select the data source. It's the same channel, so we're bridging that channel data to both. We'll tell it to expect the exact same schema that we did previously. And then we'll add two activities. One is a filter utility. So in this particular case, we're only looking at Alexa usage data. So we will select filter. We'll select the attribute that we want to filter on. In this case is request type. And request type values 3 for our data means Alexa. And we'll say is not, so filter out any messages that are not 3. And then lastly, we need to select a Lambda function. So we're going to be enriching this data, adding a few fields, dropping fields, but to add the fields, we need a Lambda function to query our DynamoDB as the other source of our data. So we'll select that. Select the Lambda function. Give it a batch size. So this says we'll process up to 10 messages per iteration of the Lambda function. And that's all the activities we need. We'll create a new data store because one for the marketing dashboard has not been created yet. And that is it. That is the entire pipeline from start to finish. Next, we'll take a look at one other thing. So now that we have the pipeline, we actually need to feed it with data. So here is a simple Lambda function that we use to ingest CloudWatch logs. We unzip them from the format. We filter them on a few specific requests. So we're dropping discover, report state, accept grant. So we really want the individual user requests. We build up a request structure based on the information coming in, and then we do an HTTP post to the IoT topic, MQ topic that we set up before. So now that we have our two pipelines created, let's put them to use. I set up the same pipeline using these exact same steps I just demoed about 4 weeks ago, and it's been running live traffic since. Both data stores have been collecting filtered and unfiltered Alexa traffic metrics for the last month. Now we want to use the data to train our anomaly detector and actually deploy it. So what's the goal? We always have to start with this because it's one of the most critical steps in the whole process. We define the insight or the result that we're trying to accomplish and let that drive our methods. In this particular case, we want to monitor Alexa usage data in real time to look for and alarm anomalous usage patterns by looking across multiple features. The diagram you see on the right is an older dashboard we built early on, which maps 3 metrics over time: success ratio on top, request volume in the middle, and request latency on the bottom. Each of these metrics tells a different part of the overall story about how our service is running and gives a glimpse as to what the current customer experience looks like. And while graphs are great, and there's only so much that can be represented in 2-dimensional space. Additionally, what happens if no one's looking at the graphs or when something goes wrong? We needed a way to monitor across several key metrics and automatically alert operational staff as to possible problems based on learned historical usage. But before we dive in to how we actually train our model, let's talk a little bit about the model itself and how we chose it. So the first question, how do we actually determine if a particular data point is anomalous or not? There are several methods, and most reference common statistical tools like Gaussian distributions. To review, for those that might be unfamiliar, a Gaussian probability distribution typically takes the form as shown on the left, where you have a single dimension or parameter indicated in yellow, and based on the historical values of this parameter, you can fit a bell curve to the data table to determine the mean and standard deviation, which defines the shape of the curve. You can now use the human subject matter experts to set a limit or threshold epsilon, we'll call it, which marks the point at which samples outside of this range are considered anomalous. And for some problems, this mechanism works very well. You can even use 2 or more dimensions or parameters, each dimension maintaining their own mean and standard deviation and epsilon values as shown in the diagram on the right. However, there are limitations with this approach, particularly in cases where there's a dependency between multiple dimensions. But now let's consider the following example. We have a data set as shown on the left with normal values shown in yellow and an anomalous value shown in red. As you can see, there seems to be some sort of linear dependence between x and y values. Maybe this is CPU usage and memory usage, where typically CPU usage scales linearly with respect to memory. But if there's a data point like the one in red, where memory usage is extraordinarily high for the current CPU usage, this may indicate a condition that's been known to be a precondition for failure in the system, and you need to flag this quickly so it can be looked at and addressed. Univariate Gaussian models struggle to capture these kinds of dependencies. Case in point, look at the examples on the far left and far right of the graph, where with the rings as they are currently defined. The samples to the far left and right have a lower probability value than the anomalous example. This is where multivariate Gaussian models really shine. Multivariate Gaussian models take these dependencies between input features into account and are able to generate a covariance matrix that can better capture and represent these dependencies as a result in more accurate detection models and complex systems. This is why we chose this particular model. We define 6 metrics which we've identified that we want to track, and we want to train a multivariate Gaussian distribution to generate a mean vector and covariance matrix that can accurately flag samples that fall outside the global parameter epsilon. Shown here is the red ring, after taking into account all the input features. As you can see in the diagram to the right, given the same sample data between the left and the right images, the multivariate model is able to adjust the rings such that the anomalous samples fall outside the epsilon threshold. So how do we go from time series Alexa usage data to train a model like this to detect samples that fall out of the range? That's precisely what Jupyter notebooks are useful for in this process. Once we have the data flowing into the data store, we can launch Jupyter notebooks to import the data so that we can start to analyze it. We ingest the raw data using pandas, which for those unfamiliar is an awesome tool to transform, filter, and visualize the data using Python. Now, rather than acting on each request independently, we choose a time interval to bend the data and evaluate our metrics on specific groupings. And for our particular case, we group entries into 15-minute bends. Then we transform the data in each bend to a single feature vector of 6 features that we're training on. We then train our multivariate Gaussian model by generating the mean vector and covariance matrix and pick a value of epsilon. And then lastly, we use these outputs of the model to actually run our model with live data, executing it every 15 minutes on the last 15-minute interval. So now let's switch over and take a look at actually all the Jupyter notebooks that went into this. So as you can see back in the IoT Analytics dashboard, there's a tab under Analyze for notebooks, and I have a number of them defined that I already have open. We can walk through each one of them. So the first thing we need to do is load the data in from the IoT Analytics service and save it to disk. And that's really all this guy is doing. So we grab the CSV URL from the data set from the service, and then download the CSV to disk so we can load it in some of the other notebooks. One of the first things we want to do with this data is actually visualize it to see what we have. So we do some general init, loading a bunch of packages that we need. We load the data from disk, and then we display it in a pandas data frame. As you can see, for every single user request, we have a timestamp, action, device ID, user ID, value, etc. A lot of the metrics that we capture per request basis. And down here, we have 1.5 million entries for the last month's worth of data to analyze. Now we actually need to take this raw data and bin it. So that's what a lot of these helper functions are for. We have a function to group all the entries into 15-minute bins. We extract the stats, so we take the totals from each of those bins and generate metrics like the total number of requests, the number of successful requests in that bin, the number of failures, the success ratio, weekday, a Boolean weekday versus weekend, because as we'll see in a second, there are usage patterns and differences between them, and then a field for flagging it as an anomaly or not. We have another function just to do that for across all 96 bins in a day. And then we have functions to actually print them so we can visualize it to do the hand classification. So in particular, we take a few days and plot them over top of themselves. And as you can see, the total number of requests tend to follow a similar pattern. And we can detect things like usage, the number of requests being too low or too high for a particular day. But we also plot things like failures. So we can see if failures are uncharacteristically high for that period of the day, as well as the success ratio. In this particular case, we're certainly going to flag this, the blue, which is from February 13th, where this particular bin fell way below 65%, and that corresponds to the spike in failures up here. We do this across all the different days of the data that we have and manually classify by us looking at it what samples are actually anomalous or not. So here's another few of them that we pick out. We run this a few more times, and again, you can see high failure rates, low success ratios, and then we manually do that for all the days that we're considering. Now that we have a list of all the anomalous examples, we need to build up a pandas data set that we'll use to eventually train our model. So we have a notebook for building a bin data set. We load in the CSV like we did before. We have similar helper functions to bin it and extract all the metrics. And then we build the data set on the date ranges that we're particularly interested in. And this results in about 2,300 rows. So this is 2,300 15-minute bins since February 13th. And then we store that to disk so we can use it in the next notebook. So now that we have the data, we import it back into this one. We can display it, see the same 2,300 data points, and then we have a simple function to label the ones that we identified in the visualize as anomalous examples, and then again save that to disk. In this particular case, out of the 2,300 samples, we've identified 22 of them, or about 1%. So now that we have the labeled training data, we're actually able to train our model. So again, we load the data from disk that we've already trained and classified, and then we display out. We have 2282 normal examples and 22 anomalous examples. We strip off the last column, which is the anomaly, giving us the 6 features that we were talking about before. And then we divide the data set up into training, validation, and test sets. A couple of things, important things to note. So the training data is randomly chosen from the data set, and then we divide it up in about a 60-40 split. So in particular, it works itself out to be about 17-18% for the validation and test sets, and that's taken away from the training data. But none of the anomalies are in the training data because the mean vector and the covariance matrix we want specific to what our normal traffic looks like. And then we take the anomalous data and spread them evenly over the validation and test set. And lastly, we split out the validation and test set separately because we trained the value of epsilon on the validation set, but then we need a test set held back to actually evaluate the trained model on data that the model has never seen before. Then there's a couple of functions to actually generate the covariance matrix and the mean vector, as we see here. We define the multivariate Gaussian function and a function to actually run the Gaussian function to generate predictions, and then we calculate a confusion matrix which gives us recall, precision, and F1 score. And then we take this and run all of our anomalies through the Gaussian function, and to get the maximum value out of here, which will give us the value of epsilon that will generate no false negatives. So everything that we've identified as an anomaly, we want to make sure that this thing will capture. And for some people, that's enough. So being able to, if I say it's an anomaly, I want to make sure that you capture similar samples. However, there is this false positives because these are based on averages and standard deviations. And in our particular case, 20 seemed a bit high for this, for 411 samples. to where we wanted to modify this a little bit, so we're fine with a few false negatives as long as we get fewer false positives, because we don't want to be alarmed all the time on stuff that may or may not be, borderline conditions. So we can actually take this and plot it over a range of different epsilon values and plot the recall precision curves and F1 scores. And as you can see, as the recall score goes up, precision typically goes down. There is certainly a trade-off, and the F1 gives you a good indication as to the balance of them. And so in our particular case, we chose a value of almost 10 to the minus ninth, which puts us in this flat space in the F1 curve. And what that results in is 2 false negatives, but we reduce drastically the false positives down to 4. And for our particular case, classes that are on the borderline, we're okay with a few missed ones because we do review it after the fact, but we also didn't want a bunch of false positives alarming us at all hours. And then finally, once we have the covariance matrix and the mean vector, we simply, in our particular case now, we have an EC2 instance running a Python script with those trained values, and then if it detects pulling 15 minutes worth of data out of the IoT Analytics dataset, every 15 minutes evaluating it, and if it's determined to be anomalous, it's sending an SNS, which will trigger a text message to myself and a few others, as well as a Slack message to a private Slack channel that we have. All right, we can now move on to our next use case, the marketing dashboard. Historically, we've had limited metrics about how all of our products are running in the field and how customers are using them. We took this opportunity to try to address that with IoT Analytics and the QuickSight service in particular. However, to best leverage QuickSight, we needed to transform and enrich the data right in the processing pipeline and store that filtered data so that it can be ingested directly from the IoT Analytics service dataset without additional QuickSight specific alterations. Some of the transformations included simply converting between cryptic data representation to more human-readable strings, such as HTTP status codes to success or fail, for example, as well as grabbing additional pieces of information from other data sources like DynamoDB, and then add those fields to add in fields like product name and model name. And here you can see on the left we have the input data that's coming in to our channel raw from the Alexa Lambda function. And then we have the output that we desired, and then we leverage the Alexa filtered pipeline that we created before that triggers a Lambda function to grab data from a DynamoDB, filter out a few fields, add a few fields, and transform a few fields. So in particular, I tried to color code this. All the white ones we left as is and passed it through. The yellow one, we actually transformed it from turn on, which is an Alexa specific request, to a simple on command. The one in green, we took the HTTP status code of 204 and translated it to success. We dropped the red values because they weren't pertinent for the marketing teams, and then we added 2 fields, so the product name or the model name, and then the product name, the name that the user actually gave it. And this is what we feed into the data store, which we import into QuickSight. So let's actually take a look at this QuickSight dashboard. So in particular, in QuickSight, we were able to import the data set directly from IoT Analytics service, and then we generated these views and then allow our marketing teams to actually modify and view these however they see fit. In particular, this is the last couple of days of usage where we're breaking out commands like on-off and set brightness, which is very interesting in their own right, such that you can see how drastically more on-off requests are as opposed to setting brightness, for example, on a lot of our products. This also gives them the ability to quickly change how this data is viewed. So we switch it to a day view and get a very different graph of how the usage tracks over time. We also have individual products broken out, so it's very interesting for them to see that one particular product is almost a 10-to-1 usage over a lot of the other ones, in particular Switch. A lot of that's because Switch has been out for the longest, but you can track this data over time to see a trend. How are our in-wall products trending, which are some of the newer ones as opposed to the plug-in ones from earlier. You have other interesting metrics like the distinct number of users, and this has been per day effectively. So you can see on average we have about 3,700 users using the service every day, and the number of devices is just under 7,000. We also have a couple of graphs that further show the disparity between on-off requests and the next one, which is set brightness. And we also have the number of requests per product showing visually how much Switch dominates. And lastly, we have a couple of top-end users where we can see a user ID over here and how many times they've issued certain Alexa requests over the last 30 days. And then we can marry them up with other tables like the device ID by user. And you can see there's a particular user that has 44 devices, a few of them that have 25. This is, again, good information for the marketing and sales team of how many users actually are using our products. And you can also watch this over time such that how many users, what's the acquisition rate of some of our products. And then we also have, we're also able to take the distinct number of users over time. So in this particular case, you can map from February to March and see that there's a decrease of 400, but then again, March isn't over yet. So we'll see how this number changes over time. And with that, I'd like to thank everyone for attending, and I'll hand it back to Kip.
Okay, thanks everyone. We hope you found the presentation useful. We look forward to seeing you guys on the service at AWS IoT Analytics. The service is currently in preview, so if you go to aws.amazon.com/IoT Analytics, you can request access and look forward for more. Thank you very much.